NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. My name is Marc Razze from JPL's Office of Communications and Education, and it is my pleasure to be your host, and thank all of you for joining us. So tonight we'll be talking about the NuSTAR X-ray telescope, which is approaching the 10th anniversary of its launch. Now, of course, most of us know that X-rays are a commonly used medical diagnostic tool, but they can also tell us a great deal about astronomical objects. Many such objects emit light in the X-ray band, and by examining that light, we can learn a lot about those objects. But as we'll also learn tonight, X-rays aren't the easiest things to observe, but they can provide some amazing revelations. So to handle the question and answer part of the program tonight is our co-host, my friend and colleague and fellow Office of Communications and Education member, Brian White. Good evening, my friend.
Good evening, Mark. Good evening, folks. First off, stay tuned to a webpage near you for more information on NuSTAR's 10th anniversary on June 13th. You can follow along with that mission or find out more information at nasa.gov/NuSTAR or nustar.caltech.edu. As a reminder, this is your space program, and we want you to be involved. We'll be taking your questions this evening. You can ask those questions by using the chat feature in whatever platform you're on, and if you don't see the chat, hit refresh, and that chat feature should be there. Lastly, if we run into any technical difficulties, please stay patient with us as we get those worked out. Now back to you, Mark.
Thank you very much, Brian. So our guest tonight from the California Institute of Technology is Dr. Brian Grefenstette, who is a principal mission scientist on the NuSTAR telescope. Brian's interest in astronomy started pretty early, and he fed that interest by working at the Smithsonian Air and Space Museum while in high school. And then he spent several summers interning at the U.S. Naval Observatory. He went on to earn a BS in physics from Stanford and his PhD in physics from UC Santa Cruz. As a postdoc, he moved to Caltech to work on the X-ray detectors for NuSTAR. And well, he's kind of been there ever since. Now he's a scientist in the High Energy Astrophysics Group. Good evening, Brian, and thank you very much for joining us tonight.
Hey, Mark, thanks for having me.
So just to kick this thing off, tell us a little bit about yourself.
Sure. So I grew up outside of Washington, D.C., and, everyone has that movie they watched over and over again as a kid. And for me, that was The Right Stuff, which is the story of Chuck Yeager and the original Mercury 7 astronauts. So I had space on the brain from a pretty early age. And when I was growing up, I had a great little telescope. And even in the muggy suburbs around D.C., it was good enough to see the moons of Jupiter and to see a pretty good image of Mars when it was up. Once I got to college, I got into working in physics labs. I started to get into sort of the science of measuring things, which is really what experimental physicists do, is we build devices and we go out and we measure things about the universe. After I finished at Stanford, I went over to UC Santa Cruz, where I got to work with my advisor, David Smith, to design and build my first real instrument that I got to build from scratch. So we built gamma ray detectors that went and flew around inside thunderstorms, where jets of electrons and anti-electrons are running around at nearly the speed of light and make lots and lots of gamma rays. So to borrow a term from David, that's sort of when I started to think of myself as an experimental astrophysicist. So once I graduated, I was fortunate enough to move down the I-5 here to LA and work at Caltech to help build the X-ray cameras for this brand new X-ray satellite that was going to launch in just a few years called NuSTAR. Now, NuSTAR, in NASA, everything's an acronym, and NuSTAR is no different. It stands for the Nuclear Spectroscopic Telescope Array. Array because there's actually two telescopes on NuSTAR. They're completely identical. So I'm really excited to talk with you about that tonight.
So what's the day-to-day look like for a scientist like yourself?
Sure. So I call myself sort of a bolts to bits scientist. So I like working with my hands in the lab. And I also write a lot of the computer software that astronomers use to take the data from the satellite and use it to make all of the images and spectra that we use to do really amazing science. So once NuSTAR launched in 2012, I got the chance to get involved back in astronomy and get involved in a lot of the science that NuSTAR is doing. Whenever you look at sort of the brightest things with your telescope or the faintest things with your telescope, you really want someone who knows all of the quirks about how the instrument works to get the most science out, most bang for your buck. For me, for NuSTAR, that's someone like me and a couple of the other principal mission scientists who got involved in all kinds of interesting science. So I get to work on some of the brightest things we do, like solar flares, to things billions of times fainter, like the radioactive ash left behind by supernova explosions. So all of this lives under the category of high energy astrophysics, which is where we're mostly dealing with X-rays and gamma rays.
So tell us a little more then, like what X-rays really are, like where they fall on the spectrum.
Sure. So let's bring up slide number 1. All right, great. So what we're looking at here is a nice little cartoon showing the electromagnetic spectrum. So in everyday life, we think about light, which is when we talk about it, with my son, it's light that comes from the sun or from a light bulb in the room. And then we use words like radio waves that carry the music that we listen to in our car and our cell phone signals. And then, we go to X-rays, which is what we might encounter when we go to the dentist's office. Now, all of these waves are actually all light. They're just different kinds of light. So astronomers are kind of like detectives, where the only information we get about the universe tends to be light that comes from a source. So what we figured out over the years, and you can sort of see this on the bottom here, is that as things get hotter, the light that they emit tends to get more towards the blue. If you take our star, which is a few thousand degrees, it'll emit most of its light in the infrared and the optical. If you take a much hotter star, it'll look bluer. And if you get a bunch of really hot material, it'll actually glow in the ultraviolet and the X-rays. So astronomers use different kinds of telescopes to look at different kinds of light to figure out how the universe works. Now, the last thing I want to point out on this slide is the top bar there, which shows you what kind of light makes it through down to the ground. Obviously we see optical light. That's the light that we see with our eyes. But most of the other light gets blocked by our atmosphere, and especially the high energy light, the X-rays and gamma rays. Our atmosphere actually protects us from all of that harmful radiation that's coming in from other stars and other places in the universe. Now, this means that if you want to study some of the hottest and densest material in the universe, you actually have to go to space, which is where NuSTAR comes in. So let's go to slide number 2. Great. So I've been working on NuSTAR for most of my scientific career. That's me in the lab on the bottom left there. We're working on calibrating the flight detectors before they were bolted onto NuSTAR. And you can see the other scientists that worked on the detectors above me, or some of us, and then the whole instrument being put together out in Dulles, Virginia. Now, before I go on, I just want to emphasize that there's a huge team of engineers, instrument scientists, technicians, electrical engineers, mission operations experts. All of those people work together on a mission like NuSTAR to make it happen. And NuSTAR was actually an international collaboration. It's led here by the PI, Fiona Harrison, who's my boss here at Caltech, who's been our fearless leader for many, many years now. And the cameras were actually built about two stores down from where I'm sitting right now. We partnered with our mission operations team at UC Berkeley. They're fantastic. And then Columbia and NASA Goddard helped build the telescopes on NuSTAR. We have international partners at DTU in Denmark, and the Italian Space Agency provides the ground station that we actually use to talk to NuSTAR. NuSTAR is flying in space, so we had a spacecraft partner, which is Orbital Sciences, which is now part of Northrop Grumman, and actually they're headquartered in Dulles, which is about 30 minutes from where I grew up. So that was one of the things that got me really excited about coming down to Caltech, was I got to work on this new space telescope. I got to actually get in the lab and get my hands on hardware that was going to space. So it was really exciting to be part of the team working on this instrument, and it was a really great time.
So what makes an X-ray telescope different from a telescope, an amateur astronomer, say, might have in their backyard?
Right. So first off, it's in space. But even if you took the little telescope I had growing up and put it in space, you won't instantly have an X-ray telescope. Let's go ahead and play movie number 3. So X-rays get absorbed by mirrors. They don't like to reflect off in a normal incidence angle. So you can't make a mirror like that. Instead, you have to make a mirror like this. So these are conical shells that deflect the X-rays just a little bit. So each shell here deflects the X-ray by about 1 degree, and it focuses down onto your camera, which has to be really far away from your optics. So the typical focal lengths here are about 6 or 10 meters or 30 feet in the case of NuSTAR. So that's sort of what is the sort of unique part about an X-ray telescope and how it's different from what you actually might have sort of with your standard experience with amateur telescopes.
So then, what is NuSTAR specifically?
So NuSTAR is a SMEX. It's something called a small explorer. This used to be the smallest thing that NASA launched into space. Now NASA launches these little CubeSats, which are the size of a shoebox. NuSTAR, the whole observatory weighed about 150 kilograms, so less than 800 pounds. And to get to space, you had to fit inside a small launch vehicle. Falcon 9s weren't really a thing back then. And what I'm going to tell you about tonight is that even though we were a small explorer, we've gotten about 10 years of really big science out of this telescope. So let's go on to the next image. So this is what NuSTAR looked like on the ground. So on the left side, you can see the whole instrument. This is the telescope and the detectors sitting on top of the spacecraft. The whole instrument was almost exactly as tall as I am. I'm about 6'3". So it's about 2 meters tall from the bottom to the top. You can see the solar panels wrapped around the sides of the observatory. And the reason the instrument was so small that it had to get to space, you had to fit inside of a pretty small rocket. So on the right side there, you can actually see NuSTAR inside the nose cone of a Pegasus rocket up at the Vandenberg Air Force Base just near Santa Barbara here. Now, the Pegasus is a fun launch because it actually launches from the bottom of a plane. You can see it strapped to the bottom of a Stargazer L-1011 aircraft there on the bottom right. The entire instrument payload is just in the nose cone, just to the far left side of the rocket. Now, being on a plane gives you a lot of flexibility in where you want to launch from. You can launch from Vandenberg, you can get your plane out to sort of almost wherever you want to go. But the volume and mass, or the weight of the telescope that you can launch, is extremely limited. So let's go and play the next movie. So this is what a Pegasus launch looks like. This is not NuSTAR. NuSTAR launched from Kwajalein Atoll in the South Pacific about 4 o'clock in the morning. We didn't have a chase plane, but you can sort of see the instrument taking off. Hold your breath while every time the plane goes up and down. The rocket gets dropped from the aircraft. You count to 7 seconds, hope that you hear the rocket turn on. There it goes. The Pegasus shoots forward and then injects your satellite into orbit. Now, I liked Chuck Yeager in the X1, but there's no Chuck Yeager in there, right? To make sure that the thing actually went off. So it was pretty white knuckle stuff while the rocket dropped away. All we saw was just it falling out at the bottom of the aircraft until we heard the confirmation from the controller that the rocket stage had ignited. So that's how NuSTAR got to space.
So you said you had a really long focal length required for this type of telescope. Like, how did you manage to get that in the nose cone of this rocket?
Sure. So NuSTAR is actually a transformer. So let's go ahead and play the next animation, number 6. All right, so this is showing what NuSTAR looked like after we got into space and we deployed the solar panels. We had figured out how to point the spacecraft. There's actually a little thing called a deployable mast that sits down between the telescopes, which you can see the 2 telescopes there, and the detectors, which are down at the bottom. There's a single motor sitting inside that canister there that's pushing out this little Tinker Toy mast that's deploying these things called bays. So the bays, once they go out, they lock into place, and that pushes the optics and the detectors apart until you get to the focal length we need for NuSTAR, which is 10 meters. So 10 meters is 30 feet, which is about the length of a school bus. So this is not a small observatory once you actually get it out and deployed into space. Now, on the ground, this is obviously an animation. We don't have any video of this happening. And on the ground, all we saw was the one little motor that's driving it. Every time one of those bays locked into place, you'd see a little blip happen. So we're sitting in the control room at UC Berkeley, hoping that we count the right number of blips and have the whole observatory deploy. So this was sort of our second really exciting moment on deploying the observatory. So I think it took about 20 minutes. That animation was sped up. It felt like it took about 2 hours. Everything went well. The mast fully deployed. And after that, we had a fully functioning X-ray telescope. So first light was looking at the bright X-ray source Cygnus X1, which is actually what we're looking at right now again, on June 28th, 2012.
That's cool. So I know we've studied X-rays in space with other telescopes. How is NuSTAR different from those other X-ray telescopes?
Yeah, so NuSTAR is the first telescope that focuses high energy X-rays. And we're actually very lucky right now because there are a lot of telescopes up in space that are studying the X-ray band. So let's go to the next slide. So this is showing 2 of the big other observatories. This is Chandra, which is one of the NASA great observatories that launched in the 90s, and ESA's XMM Newton Observatory. So these are the 2 really workhorse X-ray observatories that have been up, and they've been studying mostly the low energy X-ray sky. You can sort of see the gradient there of the band of light that Chandra and XMM see. Now, when you want to go to high energies, you need completely different kinds of cameras for that to work. So NuSTAR is the first telescope in space to actually focus high energy X-rays, which gives you an entirely new view of the universe. Now, there's a bunch of important reasons for why you'd want to look at high energy X-rays. One is that space isn't empty. There's a lot of gas and dust in galaxies, and that actually blocks a lot of the soft X-rays that Chandra and XMM see. So if you want to look down deep into the center of black holes, you actually want to use high energy X-rays. Now, the high energy X-rays and the low energy X-rays work together to really give you a complete picture about what's going on in a lot of these systems. But there are cases, which we'll talk about in a minute, where you can only do some of the science with the high energy X-rays, and that's where NuSTAR comes in.
Very, very cool. We're about 15 minutes in, so this might be a good point to take some questions. Mr. White, how's it going out there in the chat?
Oh, the chat's going great. Lots of great questions out here today. We actually just got one from Hamza on Facebook. Kind of has to deal with what you just said, Brian. How does NASA convert these X-ray images into visible ones, things that we can see?
So what we do is we generally make false color images. So we take the X-ray colors. These are obviously not things that our eyes are designed to see. That's what we make the cameras for. And we turn those colors into images that we can see and interpret ourselves. So a lot of times there are specific colors that come from different atoms, and sort of like a neon bulb is always pink. And you can take that X-ray color and turn it into something like red, for example.
Very cool. Another question that we got from Best Boy Log on YouTube, they ask, what can NuSTAR tell us about magnetars?
That is, so first off, yay, YouTube. Second, NuSTAR actually tells us a lot about magnetars. Some of the youngest magnetars that have ever been observed were ones that were detected with NuSTAR. We cover a unique part of the bandpass for magnetars that really tells a lot about the magnetic fields and what's going on in those pulsars.
Great. And we'll keep more questions coming, but back to you, Marc.
All right. Thanks, Brian. So, Brian, what gets us here tonight?
Right. So we're here because on June 13th, 2012, around 9 a.m. Pacific time, NuSTAR launched into space. So we're in low Earth orbit, which means we're only about 600 kilometers up. And we actually orbit the Earth pretty rapidly. We make it from the Santa Monica Pier to JPL in about 10 seconds. So that beats traffic. Now, that means we orbit the Earth once every 96 minutes. So since launch, we've actually done over 54,000 orbits and performed over 3,500 science observations of all kinds of science targets, from observations of giant black holes in the distant universe to things in our own solar system like flares from our sun and a high-energy aurora around Jupiter. Now, there have been over 1,100 science papers based on NuSTAR from scientists all over the world, so it'd be impossible for me to give any kind of real sampling of what NuSTAR can do. So instead, I'd like to tell you about two stories about NuSTAR's major discoveries and give you some kind of flavor of the kind of science that NuSTAR does.
All right, very cool. So what's the first one?
All right, so let's go to image number 8. Okay, so most of us don't really think about the heat that comes from our star, the sun. But what's really going on inside the star is that it's a nuclear furnace. The core of the star is busily converting, fusing hydrogen to helium. So it's basically taking gravitational energy that's squeezing the hydrogen together, and it's fusing the hydrogen into helium, which releases a bit of energy or heat. That heat holds up the core of the star and eventually comes out to the surface, and that's actually what it comes to Earth. Now, for stars a lot heavier than our sun, so maybe 10 times the mass of our sun, the center of the star can get hot enough that you can fuse the helium into carbon, nitrogen, oxygen, finally onto silicon and iron. Once you get to iron, the nuclear fusion in the center sort of takes in energy rather than releasing energy. And so it takes heat away from the center of the star. It can't hold the star up anymore, and the star collapses. When that happens, eventually it explodes in something called a supernova. Now, this is an important question for us because it answers one of the key fundamental questions of NASA that NASA wants to answer, which is, how did we get here? Right? Supernovae see the universe with heavy elements that make stars like our sun, planets like Earth, and people like us. So we really would like to understand how these massive stars explode in order to get a better understanding about how the universe came to be. Now, there's a way that NuSTAR helps figure this out, which I'm going to tell you about in a second here. So, yeah, as the star collapses, as the star collapses, sort of what happens is you get this compression of the center of the star, and what we think happens, you get sort of bubbles of material at the very center of the star. The rest of the star is acting kind of like a pressure cooker, so it's pushing in from all sides. And what these bubbles do is it kind of poke through the holes in the pressure cooker, which rips the star apart and blows the whole thing up. Now, the way NuSTAR gets at this is there's a very special kind of isotope of titanium made deep in the core of the collapsing star that lets us see things. So let's go to image number 9. So this is titanium-44, and the key point here is that titanium-44 is radioactive, which means it doesn't like to stay as titanium-44. It's got a half-life of about 60 years, after which it splits and eventually ends up as calcium-44. Now, when it does that, it releases a bunch of gamma rays and X-rays at very particular energies or colors. So the two on the right there at 68 and 78 keV. keV is an X-ray unit. You just think of them as colors. Those are the ones that NuSTAR was actually designed to go observe. Now, unlike other elements in the star, the radioactive material glows on its own. So the rest of the stuff in the star you only see when it's shock heated. And you can thinking back to the neon bulb, if you just have the neon bulb sitting there with no voltage across it, it doesn't do anything. When you turn on the switch and you turn on the voltage, then you see the neon emission. Same thing kind of happens in a supernova remnant, sort of the dead body that's left behind by the exploding star. The shock goes out and energizes a lot of the material, and that actually lets you see it. But it has to be shock heated for you to do that. The titanium emission is fundamentally different. Wherever it is, that's where you see it because it's radioactive. So it gives you a pure tracer of the radioactive ash. And the reason it's an important isotope is it's actually created way down deep in the center of the star. So it's tracing out these bubbles that might be occurring in the center of the explosion. And then you can go sort of like a CSI detective later, look at what's left on the sky and try to figure out what happened in the explosion. So let's go to image number 10. All right, so this is my favorite supernova remnant. This is Cassiopeia A. This is the leftover body of a star that blew up in about 1680. And this is actually exactly what our chat asked about a second ago. This is a false color image mixing data from the Chandra X-ray telescope and NuSTAR. So in Chandra, we're looking at emission from iron, which we've colored red here, silicon and magnesium, which we're coloring green, and the rest of the shock emission, which is in gold. Now the blue here is the titanium-44 observed by NuSTAR. Now this is way above the ability of any other focusing instrument to see. It's way beyond what Chandra and XMM can do. So this is the first time we've ever sort of seen an image of what the titanium looked like. And the minute we looked at it, we were like, okay, well, what's going on here? So the center of the explosion, sort of could have been just very smooth, just a spherical isotropic explosion. It's not, right? Clearly, we can see that the blue is nice and clumpy. We can actually trace the Doppler shifts of the blue light, sort of like a siren coming by you, changing pitch as it goes towards you and away from you, and actually get a 3D reconstruction of what's going on in the supernova remnant. And we can tell that there's giant asymmetries. There's more stuff moving away from us than towards us. So it was really an exciting first light kind of thing where we got to go look at the supernova remnant. Now, before we launched, we knew we were going to do this, right? You tell NASA, I want to build this new satellite. They say, okay, well, what are you going to do with it? Cas A is one of the things we said, okay, we're going to go look at the titanium in Cas A, and it's going to either look like a nice spherical ball, or it's going to look like the iron emission, or it's going to look like the jet emission that we see here. And obviously, it doesn't look like any of those things, right? So this was an exciting reason why you go build new observatories to get new data, so you can actually say, okay, we thought we knew what was going to happen here. We were wrong. So this was a sort of a known unknown, and one of the really interesting science results from NuSTAR.
That's very, very cool. Let's check in with the chat again. Mr. White, how are you doing out there, my friend?
Such wonderful questions. Keep them coming, folks. So speaking of new observatories, Baba Ganoush on YouTube asks, with such a difference in wavelengths imaged, how will NuSTAR be able to partner with the Webb telescope in studies to understand high redshift and high energy objects?
So even right now, NuSTAR is looking at some of the fields that James Webb will look at. So there's a fields in the north ecliptic pole where James Webb is going to look at that a lot to look for things that are varying. And so NuSTAR is going to find a lot of the black holes that James Webb is actually going to see and will help characterize those things. So it connects through the infrared light that James Webb is going to see with the high energy X-rays that NuSTAR sees. So we're looking forward to really working with James Webb over the next few years.
Well, you also said the magic phrase, black holes. We've been getting lots of great questions about black holes, and maybe this can lead you down your next path. I'm going to combine two here. So Raul on Facebook asks, could similar techniques be used to make an image of a black hole in X-ray like the one used in the EHT using a different X-ray observatories? And then Tom on YouTube asks, do black holes emit X-rays?
So the answer to the EHT question is, I don't know, which is, I think, a very fair answer. So the EHT was mostly radio telescopes. You can merge them together using interferometry in a very complex way. It would be very difficult to do that in X-rays, and certainly beyond the capabilities of what we have now. The second question of what we see, do we see X-rays from black holes? Absolutely. So black holes themselves don't emit X-rays, but as they eat material, which I'm going to get to in just a second here, they can actually re-emit that gravitational energy out as X-rays. And my office mate does a lot of amazing work studying the extreme gravity right near the edge of the black hole.
Wonderful. We'll keep those questions coming, folks. We're going to get as many in as we possibly can today.
All right. So, yeah, sorry, Mark.
No, go ahead.
Yeah, I wanted to tell you guys another story. And it sort of starts with one of my favorite quotes, which I'm pretty sure is from Isaac Asimov, which goes that the most exciting phrase in science is not eureka, but okay, that's funny. So we had one of those moments a couple years ago. So there are these objects called ultraluminous X-ray sources, or ULXs. These things are so bright that we can see them in other galaxies. And they're so bright, in fact, that people generally assume they had to be black holes. And not just black holes, but big black holes. So let me sort of give you a reason why we think that's the case. Let's bring up image number 11. There we go. Great. So this is a little cartoon that shows what happens when a material falls into a black hole. So as material falls in, it gets converted from gravitational energy into radiation, that E equals mc squared thing. And some of the energy sort of gets emitted out as light, and that provides sort of a pressure against the material that's falling in. So there is effectively a maximum amount that a black hole can eat. Black holes are on a diet. So when you hit a balance, you hit something called the Eddington limit, where you simply can't put any more matter into the black hole, and therefore you can't get any more light out. So what this means is when you have a black hole, you can sort of scale it. If I turn the mass of the black hole up, I can throw more material in there, which means I can generate more light. So if I have a heavier black hole, you can get more X-rays. A lighter black hole, less X-rays. So for ULXs, they were so bright that people debated for decades about whether or not they were black holes sort of in the 10 to 100 times the mass of our sun, eating right at this Eddington limit as fast as they can, and being as bright in the X-rays as they could be, or if they were much bigger black holes, like 1,000 times the mass of our sun, eating more moderately. Either way, generally thought these have to be black holes. So let's fast forward to January 2014. The whole NuSTAR science team is in New York. It's freezing. We're getting together to talk about the first year and a half of amazing results. I think I presented the Cassiopeia results for the first time at that meeting. And a supernova goes off in the galaxy next door. So let's go to image number 12. There we go. So this is the closest supernova that happened to Earth in decades. So this is a galaxy called M82, which is absolutely gorgeous. It's called the Cigar Galaxy. You can see it with your backyard telescope. It's fantastic. Everyone, so we're at the science team meeting. Everyone's email starts exploding, saying that this thing's happening in M82. So everyone turned around and pointed their telescopes at this galaxy for about a month to try to see any X-rays that might be coming from the supernova. Now, unfortunately, NuSTAR didn't see a lot from the supernova itself, but we did see were these X-rays from these two ULXs that live in this galaxy. Now, we knew these ULXs were there from before, and my friend Matteo decided to go make lemonade from lemons and see if there was anything interesting happening. We had this month-long data set from these ULXs. And black holes, as they're eating stuff, they can have this little flickering behavior that tells you a lot about the geometry of the stuff that's falling into the black hole. Matteo, and this shows up as little variations in the light curve. Sort of, you can see the black hole basically flickering in X-rays. So he went to look for this stuff and instead found pulsations. So not just pulsations, but enough data to figure out there was a pulsar that was orbiting something else.
You and I talked about this before. That was a big deal, right? When you guys discovered that?
Yeah, this is kind of a huge deal because black holes can't pulse. Right? In order to get something to pulse, you need a hot spot that's spinning around. It's sort of like a lighthouse beaming through the universe. But you need a surface. You need a surface that's accreting some, temperature, and black holes don't have a surface. So no hot spots, no pulsations. So all of a sudden, the whole black hole idea that these ULXs were black holes are out the door. So instead, we think this is actually a neutron star. So not something 1,000 times the mass of our sun, not 10 times the mass of our sun, something that's basically only maybe 1 or 2 times the mass of our sun, crammed into the same space as San Francisco. And this thing was spinning once every 2 seconds and orbiting its companion star once every 2.5 days. So let's go to image number 13. So this is an artist's impression of what that system might look like. You've got so this is a binary system. So you have the neutron star there orbiting a big star. It's eating material from the big star. You've got this big accretion disk of material, this pancake, as the material is flowing in, and then the neutron star sitting there at the center. So this is now an entirely new field of astronomy because we had this unique data set from these ULXs. Because we had a month of data, we can actually go find the pulsations from these things. And now we know that they're way brighter than they should be based on that Eddington limit. So there's really, we have no idea how these things are actually emitting this much X-ray light. And so a really, really exciting result.
That's so cool. 10 years in, and you've got a whole new field of astronomy to play with. That's awesome. So what's the future of the spacecraft look like?
So NuSTAR's future is really bright. So the observatory is completely solar powered. So as long as we're flying, we're doing great science. So I mentioned the mission operations team at UC Berkeley. NuSTAR is an entirely robotic observatory. So we send up a set of commands to tell the telescope where to look in the sky. And it goes and does that. We observe 24 hours a day, 7 days a week. We're still making new discoveries and learning how, new ways to use the telescope even now, which is fantastic. And there's lots of new and exciting things for NuSTAR to do in the future as even more new telescopes come online. NuSTAR plays really well with others. There's a new mission from NASA called IXPE, where we're doing a lot of observations with right now. That's really exciting. And there's a new mission that's coming out next year called CRISM that we're also really looking forward to working with. Now, one thing you may not know is that for the most part, satellites like NuSTAR are there for the entire scientific community to use. So after the first couple of years of the mission where we did all of the stuff that we told NASA we'd do with the telescope, we sort of turned it over to the scientific community. Most of the observations we do now are actually from scientists who are not part of the original science team. And that means that missions like NuSTAR remain really agile and that we can pivot to new fields like ultraluminous pulsars as soon as they're discovered. So we do this kind of thing every year, and it really keeps the observatory fresh.
That's cool. So what's your role going to be as the mission kind of continues through the future?
So one of the things I do now is, my job is to try to make NuSTAR as accessible as possible. So the great thing about X-ray astronomy is that you can do it from anywhere. I make pictures of dead stars on my laptop. All of the data from NASA telescopes are out there in the public domain for anyone to use. We make all of the software publicly available. Most of the developers working in astronomy now are working in an open source environment. And so we're really trying to encourage a lot of people from all over the world to get involved working with NuSTAR. So that's one of the things that I really like to do. And let's bring up image number 14. So this is the NuSTAR science team. This is actually from NuSTAR's 8th birthday, so a couple of years ago, back when playing with Zoom backgrounds was still a fun thing to do. And we had everyone, this is just the local Caltech and JPL group, everyone put their favorite science result from NuSTAR as their background. And the thing I want to call out here actually is that there's, a lot of undergrads and even high school students who come work with us. X-ray astronomy is a great way for people to get involved in astronomy. And it's really been an exciting thing to work on.
That's just so cool. And I know we could talk about this thing all night long, but we just unfortunately don't have time. But let's check in with Mr. White again for questions.
Of course. Something else that you should be aware of, getting lots of congratulations in the chat about the length of NuSTAR's mission. So people are cheering for you now. Luth on YouTube asks, how intense do the source of X-rays have to be able to detect them?
That's an interesting question because it depends a lot on how far away something is. So for example, when we look at the sun, NuSTAR is actually the most sensitive hard X-ray telescope that exists right now to look at the sun. But that's because it's so close. If I took the sun and I put it, at the nearest star system at Proxima Centauri, those giant solar flares would be a lot harder to see. So NuSTAR looks out and we see stars and black holes and neutron stars over a whole range of distances. So it's really something where we can, it depends a lot on how far away something is and how hot something is. That drives whether or not NuSTAR can see something.
Very cool. I swear, this is another Brian who's on Facebook, and they ask, and this is a two-part question. They actually came back to elaborate on this. The X-ray photons that are emitted, do they have mass? And the part that they were it's difficult to understand what electromagnetic energy is if it has no mass. And can you elaborate on that?
So that is sort of a junior level physics question. So photons themselves don't have mass, but they do have momentum. And so that's kind of a hard thing to understand. But there's an energy density in the electromagnetic field that they can transmit to matter when they ping off something. So it's sort of one of those complicated things where you kind of have to trust the math to really understand what's going on there.
Trust the math. Very nice. You said you kind of get involved in all parts from beginning to end of all these different parts of it. This is Aaron G on YouTube. They want to know what kind of engineering and design goes into building a space grade X-ray detector.
Lots and lots of engineering and design. This is something where we've been building these detectors here for about 25 years. So the basic parts are there's something that's a lot like the camera in your cell phone. There's something called an ASIC, which is electrical engineering. There's mechanical engineering for mounting the detectors to the electronics. There's crystallography for understanding the X-ray crystals you actually want to use. And then there's all of the parts of putting the whole thing together and doing system engineering. So there's a lot of blood, sweat, and tears that goes into making a really good X-ray camera.
All right. Matambale from YouTube also asks, how do you correlate the redshifts between each camera when merging images? Is the shift exactly the same between all the different scopes?
Yes. So the two telescopes are basically identical. There's minor variations in how the telescopes were built, but they look the exact same part of the sky. So we can actually use the data from the two telescopes as one big telescope. And that's sort of how we get more collecting area from the telescopes at very high energies. All of that titanium stuff that I showed you was the data from both telescopes merged together.
All right. We've got time for two more questions. So Mickelson Farid GS on Facebook asks, how is this going to be helpful for us here at home?
So one of the fun things about high energy astrophysics is it lets you use the hottest and densest places in the universe as laboratories, which, they're basically reproducing stuff or producing environments that you can't make here on Earth. So one example is looking at neutron stars. Neutron stars tell you something very fundamental about the nature of matter, and you simply can't make that kind of environment here on Earth. But we have them. Nature's given us laboratories to do this. Similarly, there's stuff you can test about general relativity and strong gravity from looking at the material as it falls into a black hole. So there's all kinds of ways where you can use high energy astrophysics as a proxy for doing the physics you'd like to do in your lab here, but you simply can't.
Very cool. And one of the last questions, always fun to ask this, do you have any advice for anybody who wants to get into this?
Yeah, so I started off doing astronomy, went to physics, went to high energy astrophysics, and back to astronomy now. I think the major thing to realize is there's not one true way to get from, if you're in high school, to get to a point where you're going to be working as a research scientist. A lot of it is following what you're interested in and getting involved. So when I was in high school, I got involved in the local astronomy club, and that sort of propagated through when I went to college, and I got to go poke around in different labs and really get involved there. So I would say it's taking advantage of whatever opportunities you can to really get involved and follow the things that you're really interested in.
Very, very cool. Well, thank you guys both very much. Before we wrap it up tonight, Brian, do you have any final thoughts for the audience?
Well, first off, I'd like to thank you and Mark for having me here tonight. I've had a really good time. I could literally talk for hours about all of this stuff, and I have. You can ask my friends. So if you do want to keep up with NuSTAR, like Brian said, you can find all of this cool stuff that NuSTAR does on the NuSTAR webpage, which I don't know if we're doing it in the bottom third or not, but it's nustar.caltech.edu. So we try to keep that updated with all the new results that are coming out. We also get shout outs from NASA Universe on Twitter. So you can follow along there. And then there's a pretty good community of astronomers who like to talk about what we do on Twitter. And so if you can manage to find us, then we're more than happy to talk about all of this stuff in the future. So I hope I've been able to share some of my excitement about all this stuff with you tonight. And I want to thank the chat for the great questions.
Oh, Brian, seriously, thank you for, everything. You're sharing your knowledge, your enthusiasm. We're really glad, obviously, that, you could come and spend some time with us tonight. So we know it's a bit of a commitment. So again, we're grateful. So folks, that's pretty much all the time we have tonight. So I want to thank both Brians for all their work putting this together, the crew behind the scenes that make this all possible, and of course, all of you for tuning in for your fantastic questions tonight. So take care, stay well, and we'll see you next month. Good night.